let's see how this all plays out with a worked example. We'll consider a local reference frame where we initially have these two non-zero tensor elements, xxz and yyz, and we're asking what happens if we want to rotate our reference frame about some angle phi. And the rotation matrix for that is going to equal the following: cosine phi negative sine phi 0, sine phi cos phi 0, 0, 0, 1. And we can get that just by setting theta equal to 0 and phi, or psi equal to 0 in the full generalized rotation matrix that we had, or here. Okay. So if we do this rotation operation, let's ask first how that affects chi xxz. And I'm going to change my pen colors here so I can keep track of a few things. And I want to know what is chi x z in the rotated reference frame phi, and how does that relate? It's going to have two contributions. It'll have the initial contribution from xxz, and then because you're rotating the reference frame, there'll also be an additional contribution from the value of whatever chi yyz was. So let's consider first the contribution from chi xxz in the initial reference frame. Darn you, thought I had it. And that's going to be, we're going to pull out the elements of this rotation matrix. Now we know we can evaluate the full 27 by 27, but we're just going to look at it one element at a time. It'll be a little bit easier in terms of bookkeeping. We're going to ask what is the element of that 27 by 27 Kronecker product of three rotation matrices that connects this particular initial tensor to this particular final tensor. And we'll get that by considering first the rotation matrix that connects these two, so that'll be R, X, X. And then the next one will be the rotation matrix that connects these two, which will be R, X, X again in this case. And then finally the rotation matrix that connects these two. All right, and then we're also going to have an additional contribution from chi y. Y z. Oh, let's go back to keep any. All right, and that, by analogy, I'll skip the color coding on this one just for simplicity. This will be R xy, R xy, and R zz. So if we evaluate what all of these are, given our rotation matrix here, we're going to end up with chi xxz 0 times, this is the xx position, so I'll have a cosine, cosine, and 1. Cosine squared phi plus chi y yz in our initial reference frame times xy is this one, so I'll have a negative sine phi but squared, so that'll be sine phi. We can repeat the same thing for chi y yz in the rotated reference frame, and that's going to give us a contribution from xxz initial, and now this time we'll have the sine squared here, plus chi y yz, and then this will be cosine phi. All right, but it turns out that we're not entirely done, because there's also two additional tensor elements that can emerge from azimuthal rotation in this sense. And those are the ones that look like chi xyz. So if we include those as well, we get something that looks like this. Let's first consider chi xyz in the rotated reference frame, which wasn't initially present, but can be present in this rotated reference frame. We'll have chi, oh, I'm out of ink. Okay, let's see if this works now. So I've got chi xxz 0 times, what do I have? I have an xx, so that'll give me a cosine phi, and then I have a yz, or sorry, a yx, and that will give me a sine phi. So the total is going to be sine phi cosine phi plus chi yy 0. And now I'm going to have a xy yy zz. So xy yy, that will give me a negative sign. I'm going to change this to a minus sine phi cosine phi. And then finally we'll have an analogous operation for y xz. And it turns out that this one will yield exactly the same thing as we had before, or exactly the same thing as xyz, because we're projecting the same tensor elements just in a different order. Okay, so a couple of interesting things. We have a couple of things to note. The new tensor elements have contributions from many existing initial tensor elements, and tensor elements that did not exist can emerge in this rotated reference frame. And that's a good place to stop for now. Oh, actually, I take it back. That's a terrible place to stop for now. I want to point out a couple of additional things before I let you go here. The first is that tensor rotation is not limited to second-order nonlinear optics and processes of rank 3. These can easily and directly be generalized to any arbitrary order of nonlinear optical interaction, including four-wave mixing in cars and third harmonic generation, and extensions to 5-6 wave mixing. However many waves you want to mix, you can describe this tensor rotation in an exactly analogous vectorized format. So it's quite handy when you're talking about high order effects. All right, that's a good place to stop.